Hello and welcome to this Aerospace Testing International webinar, Automated Inspection for Aerospace using computed tomography and digital radiography. Our presenter today is Rahul Alreja, the Director of Global Sales and Marketing for VJ Technologies, a leading global provider of X-ray inspection solutions for quality control in a wide range of industries throughout the world. Rahul and his team at VJT are involved with bringing advanced technology, robotics, automation, and computer machine learning to a variety of industries, including aerospace, specifically targeting quality control and product flow. The author of several technical papers, Rahul gives presentations around the world about the latest advances in the field of non-destructive technology, an area where VJT is constantly pushing the technical boundaries. Rahul is here today to talk to us about automating the inspection of computed tomography and digital radiography, something that can be used to improve quality and efficiency. Rahul's going to give his presentation shortly, so please do post any questions you have while Rahul's presenting, and we'll answer those at the end of the presentation. Your questions won't be seen until they're published at the end. Rahul, over to you.
Thank you, Ben, and good morning / good afternoon / good evening, because I believe we do have a global audience. So thank you all for taking the time to kind of join us, and hope you get something out of it. So we can just kind of dig right in. I figured just to kind of give you a brief kind of very brief understanding of who we are and why you should actually listen to me. We've been doing X-ray technology and pushing the boundaries for X-ray technology for over the past 30 years, close to the past 35 years now. We're a leading provider of digital X-ray inspection system solutions and services to a wide range of industries, aerospace being one of them, automotive, electronics, high energy. It kind of runs the gamut. We have 4 divisions. Specific division that I'm in is technologies, which is primarily looking at NDT for industry. But we also have an electronics division that looks at electronics, X-ray that makes X-ray components, and inspection services. We do have locations all around the world. We've built these up over the past 30 plus years. We do have a whole bunch of very technical PhDs, masters, lots of engineers stationed all around the world to be able to handle any kind of problem for any of our customers all around the world. Anyways, speaking specifically about VJ Technologies, which is the division I'm with, a division that's primarily looking at a lot of this automation for aerospace via CT and DR. We are specialized in standard and custom CT and DR systems that we automate. There's a couple kind of systems there on your screen. What we're really known for is our software, and you'll find that from anybody within this industry, actually. The software is really what separates everyone else out. The hardware components that, for the most part, stay relatively similar. It's actually the software and the imaging capabilities and image processing abilities that usually differentiate all of us. And, what we bring to the table is a little bit more custom than anybody else when it comes to our design approach, when it comes to our software approach. And you'll see some of that throughout the presentation, especially as we talk about automation, because having the ability to be able to customize the look and feel and customize the flow of a system is key in delivering an automated kind of experience for a customer. Anyways, so I'm talking about automation, and I guess the question is, what does it mean? What are we talking about when we talk about automation? Typically, a few things come to mind to people. Is it automated analysis? Traditionally, that's what a lot of people look at, looking at what kind of analysis would we call ADR, right? So you're looking at automatic defect recognition, or looking at X-ray images and trying to see if you can detect porosity, or if you can detect inclusions, you can detect a seam, the width of the seam, dimensions or metrology if we're talking about in CT, porosity and cracks. Um, so we have the way of doing automated analysis via software and image processing to be able to bring that out. But there's a whole bunch of other things that actually get covered under automation, which sometimes people don't necessarily think about. And I think it's really important that we talk about these. Um, Part identification is another one. Most of these X-ray equipment, uh, systems and solutions that we deliver, they handle a variety of different parts. Now, you want the system to be able to be intelligent enough to use whether it's cameras or RFIDs or barcode sensors or whatever else you might have to be able to identify which part that we're looking at, which part the system should be looking at, and how it should analyze it. You can teach all the techniques that you want to a system, but if the system can't identify which part is necessary, then you're going to have a huge bottleneck because then the operator has to be able to tell the system each time what kind of part it is and which technique to use. So we look to use cameras and a whole bunch of other things, which I'm going to show you soon, in order to do part identification, which actually aids in automation. What about part handling? So part handling, do you use robotics? Do you use conveyors? Are you manually placing parts into the system? Do you have lift assists outside the system for heavier parts? Now, are the parts coming from the top? Are the parts coming from the side? There's a whole bunch of things that need to be looked at from part handling. And all this goes into that automation side. So it's not just X-ray image analysis. All these kind of factors need to start being looked at for automation. What about image archival and image alerting, right? So, especially in the aerospace industry, especially for the primes, you have to save images for a number of years, sometimes 7 years, sometimes 10 years, depending on, if it's military defense applications, it could be forever, essentially. Previously, this all used to be film, at least in the X-ray world, used to be all film, and you have, cabinets and cabinets and storage closets full of film that I've seen at some of these defense installations. Now, obviously, with digital, we have the luxury of using hard drive space. But again, how much hard drive space do we want to be able to use, and how do you want to archive it, and how do you want to be able to retrieve it? So all these kind of factors have to be considered. And then this last thing, which is something I'm going to be talking about a little bit, collision avoidance. So once you go into fully automated type systems, especially with lots of robotics, and like I mentioned earlier with part identification and handling, using vision systems, using robotics, the problem now gets into being making sure you don't damage the part as you're imaging it, especially if you have a variety of different parts. So collision avoidance becomes key, ensuring that the parts don't get damaged within the system or within the unit that you're building. So all these factors start getting looked at when you look at automation. So, like I said, all of these factors are things that we have to look at. So, I figured the best way to kind of go through all this is just to give you a bunch of different kind of case studies and applications that we've looked at, where we've had to consider different aspects of automation. And as you guys go on your journeys, and maybe you're looking at X-ray equipment in the future, these are just things for you guys to consider before you kind of look into an X-ray, piece of X-ray equipment, because it's an expensive tool, but it has to be able to give you what you want out of it, and it has to be able to make your life easier in order to not even, not just to satisfy your company's objectives, but also to make sure that you're meeting all of your specs and all of your tolerances that you're allowed. There's so many factors that have to be considered. So here's an idea, right? So this is system design. This is the problem statement. This was a custom composite engine shroud for the Boeing 787 Dreamliner. It had 300 plus locations of welds. Each weld had to be inspected, and there were multiple parts. So the system design had to take into account that there were multiple part types, but because it's a shroud for a 787 Dreamliner, it's a production type of part, so it has to be able to be repeatable. The idea is that this system can do multiple of these parts day in and day out and always do it the same way because it's 300 plus weld locations. So our solution used robots, but we used 2 robots actually to be able to do it. One robot was holding the source and robot was holding the detector. And using software to kind of hold the source and detector steady and in line with each other and correlate their motions, we were able to program it for 300 plus degrees, 300 plus images per part for all the weld locations that were there. As you can see, there's a turntable on the bottom as well. So the part actually rotated within this vault. And we were able to program that turntable and every single motion of those robots into one click for the operator. So the operator just had to press start. And the entire sequence would start where the part would be loaded onto that cart, placed carefully by either by operators or by a robot, enter into the vault. The X-ray imaging would start. The entire process took about 2.5 hours to do the complete imaging. Every image would be taken, every image would be properly annotated, and then spit out for review. This wasn't an ADR application, so there was no automatic defect recognition built into this, but it is a possibility, especially as you look at larger kind of complex parts, especially with tremendous amount of shots that you have to take. It's a little bit challenging on the aerospace side. I'm not going to lie. It's a little bit of a challenge to do ADR, especially because you're looking at very, very fine, typically very thin, less dense materials, and you're looking for small kind of problems within these. So you do have issues with contrast, especially in X-ray imaging. You do have the problem where you're going to have a lot of false negatives. It has, depending on the application though, there are certainly some ADR possibilities, and we're going to talk about that a little bit later. But this one didn't have ADR, but the idea was it was a fully automated inspection that just kept spitting out X-ray images and 300 plus per part and fully automated. All right, so let's see. Now, here's another very unique project that we have. This is currently something that we're looking at. It's to inspect F-15's aircraft. It's actually looking at the wingtips on the back, which is like the fins on the very back. But being able to do that is a challenge. Obviously, you're going to have overhead gantry style system that's being built, but what okay, let me just show you before I go into it. The idea is that you have repeatable and automated imaging of this F-15. Now, this is F-15s that have already been built and they're in service and they're coming back from maintenance. They're coming back for a whole variety of different things that have to be done, increasing their service life. And now the question is, how do you automatically inspect these? So we have a dual kind of robotic gantry system that we are building. Those are pedestals that robots will sit on. They're inverted. And this is one of the ways that they will look at one of the views on the tip. But we also have to do the vertical stabilizers, which I'm going to show you now. So the vertical stabilizers also have to be inspected. So now the key to all of this is, of course, you're using a lot of robotics, but because it's this actual built aircraft, you can't always guarantee that it's going to be in exactly the same spot every single time. Now, how do we ensure that the full robotic inspection can occur? It can occur in relative space. So you can't define absolute positions for the robots because the plane could be, a couple, half an inch to the right, half an inch to the left, half an inch forward, half an inch back from part to part or from plane to plane. Now, how do you ensure that you can still do an automatic technique? Because once you get registered on the part, it should be the same kind of imaging. So you scan each part from a matrix style, boom, 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 across each fin. but now you have to ensure that you can actually correct for that little human error that might be, plus or minus half an inch or plus or minus 1 inch of the positioning of the plane. So this is where collision avoidance comes in. So what we're doing to do collision avoidance is we're actually starting to build a digital twin of the part, so the F15. So this is showing a digital twin on another kind of system, but just to give you an idea, we are building a digital twin using hardware that's going to be positioned in the vault each time. So it's going to be a LiDAR kind of sensor that using basically electric vehicles are starting to use this, like Tesla is starting to use this, and that's how you do your autopilot. But we're using the similar kind of sensor, a LiDAR-based sensor, which is pulse that are going to be going several times a second in order to update the positioning of the actual part in the space in the vault. So the actual aircraft in this in the vault, plus the position of the robots and the position of the X-ray source and the detector. So we're doing this by creating a digital twin using this kind of LiDAR sensor, then building in process control measures into the robots. So ensuring that the robots have, based on the digital twin and based on the actual positioning of that specific aircraft at that specific time that this inspection is being done, ensuring that we create boundaries around that plus or minus kind of tolerances around each exposed surface of that aircraft, so that you ensure that the robot never actually touches or impacts upon the aircraft. And if the aircraft happens to move even during this, so it kind of locks into chucks and it locks into place, but who knows if something happens and the aircraft happens to move, because of this LiDAR sensor that we have and this real-time updating digital twin, that new position will be recorded, and you're not going to damage the aircraft with the robots with this automated sequence. So this is a tremendous amount of machine learning and AI kind of built into this LiDAR that we're doing here to ensure that the part doesn't get hit, which is $1 billion aircraft in this case. So imaging is another side. Like I said, automated image analysis is part of what we look at from automation. So now that we're looking at imaging, we have, like I mentioned, we have a bunch of different image processing filters that we've developed over the years that enable us to better understand what's going on inside the X-ray image that we see. We use 16-bit detectors mostly in the aerospace world. This gives you 65,000 levels of gray. The human eye can not discern that many levels of gray. The human eye can discern maybe 20, 40, depending on, the eyes that are looking at it. You can't discern 65,000, especially when you're looking at lightweight materials, especially when you're looking at lightweight materials and you're looking for faint cracks or faint kind of defects within these. So how do you kind of enhance the contrast so that you can help assist the operator in bringing out the defects and understanding what's going on in the part? So what you're seeing here is a little loop. That's the raw image there. This is our gold standard was 80E for a long time, but now we've actually looked at 80E noise reduction. So the problem is when you do image enhancement, you not only enhance the signal, which is the actual part, you actually also enhance the noise. So you get blurring, or you get this kind of not blurring, but you get this kind of patchy effect, right? So you have like kind of static almost in an image. So how do you remove that static, which is just noise that's been enhanced? So that is noise reduction that we've kind of developed, I'd say, over the past couple of years, and it's getting more and more prevalent. This is because of the horsepower that we actually have with new GPUs that have been coming out. So we can actually use the GPUs to do the noise reduction for us. So there's some more examples here. This is a weld here, looking at the raw weld here. Now you're looking at ADE. Now you're looking at noise reduction. So the noise reduction actually assists in being able to read the quality of that weld and bringing out the flaws and the defects while ensuring that the noise doesn't get enhanced. We should have another example here. So these are components, electrical components that we're looking at between raw, ADE, and ADEN, which is noise reduction. So this is another method of doing automation, which is being able to automatically enhance images and being able to bring out the defects and the flaws within those images to assist the operator in being able to read and discern the quality of those images. This is especially useful for operators who will get operator fatigue or eye fatigue looking at X-ray images day in and day out. There's another one, I believe. Yeah. So this is noise reduction and image processing and how we've been able to kind of look at that and assist in making it more automated. So now you look at CT imaging, which is, the new hot thing that everyone is starting to look at, especially in the aerospace world, because you do have complex shapes, complex geometries, and complex materials, sometimes multi-material, whether it's carbon fiber, titanium, and now you're trying to do detailed analysis of this and looking at really, really small defects in 3D space, primarily because you're going lighter and lighter weight to increase fuel efficiency, and the defects become more and more catastrophic as you go lighter weight. But they become harder to discern and harder to measure because you have less material where they have to show out. So you have less margin for error, let's call it, when you design these parts. So CT has become this tool where you can actually study the parts in 3D and start discerning whether the defects are closer to the surface, closer to the root, and ensuring exactly where the defect is, especially in complex geometries. So right here, this is a 3D printed carbon fiber bracket, 4 legs. What you're looking at is we're down to, micron kind of resolution, a couple of microns here, a couple of microns there, to look at what's going on within the carbon fiber inside. You can actually see what's going inside the weave of the carbon fiber and start measuring out porosity and defects and discerning where they are on the part. So that becomes key. And now you can actually start color coding them based on severity. And obviously red is probably pretty bad. So this is actually at a joining part right here. I'm not sure you can see my screen, but you can start color coding it. And this becomes an automated kind of analysis tool that are built into these CT viewing softwares to be able to analyze the porosity and be able to bring it out and highlight and create reports. You also are doing dimensional metrology now, fully automated again with CT. So right here, you're looking at a part that I'm not allowed to really tell you what it is. It's a metallic part, and we're looking for tolerances that are within a couple thousandths of an inch. So what you're seeing here is spacing between the two inside brackets is 1.393 inches. Here you have spacing between the two pods of 1.084, starting to measure thicknesses and starting to measure differences between walls to be able to see how these parts exactly fit. Again, this gets fully automated. So now you can actually start creating 3D meshes of the object. You can actually take CT scans and be able to 3D print them or create CAD models from these CT scans and do finite element analysis or any other kind of analysis you want based on actual parts as opposed to as design parts. So you can actually use actual CAD models from the parts that you've actually built or 3D printed and be able to run your analyses on those fully automated again. This is actually a piece of a wind turbine right here. And what you're looking at is in the middle, you have glass surrounded by carbon fiber weave. And then on the end here, you have different kind of materials of foam and carbon fiber and glass primarily. There's some fiberglass as well. And what we're looking for is within all of those different materials, we're still looking for porosity. We're actually looking for, as the carbon fiber is kind of woven around the glass, and the fiberglass is woven around, you're looking for little gaps in its layers essentially that are built around the glass, and you're looking for gaps in those layers, which is impossible to see using any other technique. Whether you look at DR, which we tried, whether you look at UT, primarily because of the different materials that are actually present, you can't actually determine if there are flaws, and if there are flaws, where the flaws are occurring. So the only way, we did a long study for about a year and a half on this with one of the leading manufacturers of wind turbines, and we determined a high energy CT technique was the only way to actually be able to penetrate and be able to discern what's going on from layers to layers. So while a 600 kV source was actually able to penetrate the part, the problem is it would have taken about 26 hours with a 600 kV source to be able to do the CT on one turbine. We had to bring that down to about an hour and a half. So we had to move to higher energy. Of course, higher energy brings with it its own issues. Of course, it's more expensive. There's bunkers that have to be built and faults and higher weight. However, we were able to bring that inspection time down into an hour and a half, and be able to analyze the part and be able to pick out exactly where the flaws are. And especially because we were using high energy, we got a tremendous amount of flux going through, so much more contrast, which is very important in these lighter weight materials. Right here, more metrology, and actually comparing CT scan metrology with actuals. So using calipers and or really finely tuned kind of calipers to be able to ascertain that the CT scan that we're running, and the metrology that we're actually doing with that CT scan is able to be validated in real life, using real data. So these were very thin wires, and we're looking for submicron voxel size, in order to be able to determine the surface of these wires, and then be able to measure the diameter. So if you can look down here on my table, uh, these were the measured results from the CT scans on the left, and on the right, you have the caliper measurements. So the thinner ones were obviously a little bit more challenging. That's just the nature of how it is, but we are still within a 1 or 2% of actual. So the measurements correlated between 0.1 to 2.0%, depending on the diameter of the weld. So, or the diameter of the wire, apologies. So we're able to use CT and then correlate that data in real life, on really thin, really low contrast kind of work, using very high resolution imaging, and determining the correct imaging parameters to be able to bring this out. Again, so one of the things that goes hand in hand with automation is ensuring that what you are inspecting is actually what's happening in real world, and in using, whether it's RQIs or radiographic quality indicators, or IQIs of some other type, to be able to repeatedly check and measure that the system that you're using is actually giving you correct data. This is especially important in the automated world, because there's a tendency that, oh, it's automated, it's using robots, it's using greatly calibrated turntables, and it's sitting on a granite base. We're fine. We don't have to worry about it. But you always do have to worry about it, because there are things that happen, whether you're looking at forklifts, or you're looking at other kind of heavy machinery that may be operating, that can actually drive things off just by a hair, and that can actually start having serious impacts within your measurement capabilities or your metrology capabilities. So especially as we build this out as automation, and automation comes into play, it's very important that we have tools to be able to periodically check on the validity of that system. So I wanted to, we've been talking a lot about automation, whether it's robots, whether it's automated analysis of X-ray imaging, whether it is looking at metrology or measurements or CT data. Now, how about we combine all of those things, right? So here you have something that our partners in Germany developed. Is called RoboCT. So using 4 robots, there's 2 sources and 2 detectors that are all moving in synchronous motion to actually be able to inspect really large components. This is actually built for an entire automobile. This is built for a BMW, the ability to be able to do a full CT scan on the entire car, and being able to. This is in actual use by BMW for production work, and being able to validate what they've built using CT data in automated kind of technique, in automated fashion. So let me give you a couple of looks at what's going on here. So as I mentioned, there's 2 sources and 2 detectors, all of these moving in fully synchronous fashion. And looking at right here, you're looking at the windshield and you're looking at the construction of the windshield and the layers in the metal. One of the challenges with this is that obviously you can't really fit fully underneath the car and be able to do a full 360-degree kind of view of the car and be able to fully inspect it that way. These are fully assembled cars. We don't have a rotating gantry in this case to be able to spin around the car, and we can't really spin the car on an axis. So that's why you're using 4 robots, multiple robots, to be able to get as many angles as you can of a part. So you're actually combining not just robotic automation and CT reconstruction and CT analysis, but you're also doing limited angle here. So you're looking at limited angle CT and being able to take data and use your previous knowledge of the construction of the part or how it should to be able to kind of fill in some of the gaps. So what you're actually going to see here are CT studies. So on the top, this is the same part. These are rivets that are installed in the door of the BMW. So on the top, this strip of rivets was done in the lab, and it's nice and clean. You can actually see the rivet, the quality of the rivets, etc. In the middle is a study that we did with RoboCT using 240 degrees of projections. So instead of being able to do the full 360 degrees, we were only able to capture 240 degrees and then use a priori data, which is previous knowledge about the part construction, to be able to fill in some of the missing gaps. On the bottom is 125 degrees. So you're taking half of what was done in the middle one and you're able to reconstruct it. And that's the quality of CT reconstruction that we're able to come up with on these rivets. So as you can see, yes, there is a little bit of a difference when you go from full lab and being able to do full 360-degree kind of reconstructions or projections and then reconstructions on that. And as you go down from 360 to 240 to 125, there is some difference. However, the beauty is we can actually now do CT on fully constructed automobiles or any other large part. In the aerospace world, there's tremendous amount of large parts, especially lately as we've been doing the light weighting. We're able to do CT on that in real world conditions and be able to get phenomenal amount of data. If you look at those rivets down there, able to see the surface of the door. Actually, you can actually see the layers. It's a little bit faint here, just because of the presentation. But when you're looking at this on a high resolution monitor, you can actually pick out the different layers that are here, and be able to do actually some dimensional checks as well, being able to measure the gap between the layers and measure how much of the rivet has actually penetrated, measure the root of the rivet, and be able to ensure that it meets your demanding quality specifications. And this, again, is with limited angle CT, because you can't go full 360 degrees around a door or one of these pieces. So using robots and being able to kind of program the robots with software know-how on the back end, you're able to do more detailed analysis of this than was ever previously capable. So that is that brings us to near the end of my presentation. We covered some ground on automation and looking at not just automatic analysis using image processing or image algorithms to be able to bring out defects, but also looking at how systems have to be designed and how robotics and vision systems and LiDAR sensors are being able to be used, all in combination with each other to be able to do things that weren't possible even 5 years ago. The advances in computing technology, computing power, the advances in software analysis, the advances in machine learning and AI have enabled a tremendous kind of growth in this sector. And what we're seeing is just the beginnings of that kind of coming out as we design some of these systems and are solving more and more challenging kind of applications. As you saw from that F15 inspection, as you saw from this RoboCT, combining software, combining the machine learning side, combining the robotic side, and combining the vision side to be able to get really close to more and more automated kind of inspection from small to medium to large parts.
That's great, Rahul. Thanks. If anyone's got any questions about that presentation at all, now's the time. Now's the time to post them, and we'll get to them as and when. I guess if that's all right, Rahul, I'll ask a few questions. I found that really interesting. Thank you so much. Great overview of the capabilities of what you guys do and some of the different range of solutions that you can bring. I'm going to start with the last example, which wasn't actually an aerospace one, but I think everyone would have found fascinating nevertheless. Is that the largest machine installation that you guys have handled? I mean, and why are they doing that? BMW seems a bit over-engineered.
Well, the Germans are sticklers for the quality of their cars, absolutely, and BMW is absolutely one of the leaders in terms of bringing new technologies and bringing new kind of modalities to be able to perfect their and improve their quality time after time. One of the things that they're looking at with that specific system is to actually be able to test cars as they come off the production line. Then they run they run them through whether environmental conditions, they run them through racing conditions, they actually use them in real world and bring it back and actually do another scan of them and want to see what the impact of what test that they were running is actually on the car. So as they're doing future construction and looking at building out, whether they're testing out new materials and new kind of techniques, they want to see what the impact is of taking that car and running through, I don't know, going at 160, 180 miles per hour in the wind, in the kind of storms, and then bringing it back, whether they do some impact testing on the car, and they want to see exactly how much crumple zone has been used and what's happened to the structural rigidity of the car. But they want to be able to do it without moving the car, so you're not, once it's brought in, the car is stable, so that you're not introducing any new kind of fixtures that may not have been done when they actually did their tests. But now that they brought it in, they want to be able to inspect it just like to like. And as far as we go, we have delivered systems that can inspect automobiles and even larger. We have, as you saw, we are working on the F15, which is a little bit larger than an automobile. We've done systems to look at pretty large objects, actually.
Yeah, I found the F15. We've got a few questions coming now, which is great. But yeah, the F15. Is that all up and running at the moment? I mean, how often does an F15? It was just the tail, right? That you're scanning, or
this is so the specific application now is for the tail section, looking at the fins. But there are there are certainly ways that that system can grow to be able to cover other areas of the F15. The specific one was for the fin and the stabilizers at the end.
And that was a periodic inspection thing, right?
Correct. So that's actually being commissioned by the Air Force
Yeah.
to be able to look at their F-15s that are in use.
Man, and the collision avoidance system, that to me seemed crazily complicated. That's hard stuff, right? I mean, is that the most difficult part of a project like that? Or
That is not an easy part. I would say we are actually we're actually partnering with an organization that specializes in looking at collision avoidance side. Our whole ethos is that we're by no means the experts at everything, but we will bring the experts in when we need them. So we know what the end solution has to deliver to the customer, and then we will work with whichever experts we need to bring in to be able to assist us to get there. So that collision avoidance side of it, it's actually a robotics company that's based out of here in the U.S. That
right.
we're working with to be able to tie in what they've developed with our end solution that we want to be able to deliver for the F15.
Still, I mean, you're integrating it all together. So I mean, that's
Yes.
that's the key thing, right? Okay, we've got some questions in there. Let's go through some people that are probably much cleverer than me. Let's see what they're asking. Adrian Login is asking, do you have non-proprietary voxel level data sets that you can share with the public? His interest is in post-CT measurement, the structural analysis aspect.
That's a good question. So we do have some voxel level data sets that we could share and kind of work with you on. I see that you want to look at post-CT measurement, structural analysis side. That's a huge kind of area of interest for a lot of people right now, is doing that kind of structural analysis and being able to look at CT data and then be able to measure that in real world afterwards and ensure that, first of all, the data matches what you're doing and the correlation is there, but then be able to do, like I said, other kinds of analyses based on the CT data set. So we do have voxel data sets that we can share. It depends on what your kind of material you're looking for, object you're looking for, but you can certainly reach out and we can kind of talk more about that. No problem.
Okay, he's got a follow-up question here on the F15 fins. He wants to know the resolution of the scans that you're doing. Are you allowed to say that?
I can tell you that it is more than 100 micron, less than 500 micron. But I can't tell you exactly what the resolution is. It also depends on the magnification. But most of the scans are typically in that 100 to 125 kind of micron resolution.
Okay, thanks. We got a question here from Pradip Acharya. He wants to know if your company is applying any machine learning algorithms for to detect detection in CT images, and if you are, what are you using?
Yeah. So we are doing. We have actually 5 studies right now for machine learning, looking at defect detection in CT images. There's different types. One is for there's a couple for metrology side, and there's a couple for actually highlighting or bringing out porosity and cracks, not necessarily being able to measure them. So there's a few different studies on each side. As far as the specific algorithms that we're using, I'm not sure I know that well enough to be able to tell you. I can certainly put you in touch with our kind of software team that's doing that. I don't know the names of the exact algorithms that they're using. I do know. Yeah, I don't want to make a fool of myself, so I can certainly get my team to answer that question for you in a little bit more detail.
I'm sure. Yeah, we can get back to Pradip on that. There's one here from Sanford Kumar. He wants to know: is it possible to detect foreign objects in composites using the ADE-N technique that that's the noise reduction thing you were describing in the presentation?
And that's a very good question. And yes, we can actually detect foreign objects. Obviously, it depends on so X-rays and even our ADE-N kind of image processing. It depends on the contrast difference between the base material and the foreign object material. if the foreign object material is very close in density to the base material, it gets harder and harder to detect. But for the most part, we are able to detect kind of foreign object or FOD within carbon fiber. Um, and ADEN is actually especially useful for that. So I would have to say yes, and but it with a small caveat that it depends on the nature of the material itself.
Okay, great. There's a question here from Louise Alexandria Teresa. It's along the lines of something I was wondering actually, to do with the cost benefit of this type of equipment. He's asking that this kind of automation looks great for a production line where these repetitive quality tests, this QA stuff, but to an operational aircraft um, with scheduled maintenance inspection, such as the F15. I mean, how reasonable is it in terms of cost investment? Is there a payoff there that can you talk around that?
Yeah, absolutely. It's a great question, and the payoff actually is in longevity of use of the aircraft. So the problem is they're not making F-15s anymore. They've kind of moved on to other aircraft since then, and but there's no reason that the F-15s can't be used for the next 5, 10, 15 years if they're properly kind of maintained. The
Sure.
problem is there's not really spare parts being made for those aircraft. There's not really any kind of development work being done on those aircraft. So the idea is if you want to improve that longevity of life and be able to use it for longer, you have to be able to ensure that you're inspecting it correctly and inspecting it within a certain amount of time frame, because it's kind of useless for the Air Force to have F-15s that go in for maintenance and then they come back like 8 months later after their inspection. They'd like to have them back out in the fleet as soon as possible. Now, if you do a fully manual inspection, which is possible, yeah, you might take a couple months to be able to inspect all of it. But if you use the automation side, you can actually get it back out within a couple of weeks, and you're ensuring that you're not kind of damaging the aircraft, which is rather expensive at this time to replace. So the cost benefit is not necessarily just from a production line kind of basis. It's ensuring the longevity of that part and ensuring that it's out of service for as minimal amount of time as possible.
Do you have systems in use with commercial civil airliners
We
in
do.
that sector?
We do have
Yeah.
for commercial civil. We it's kind of funny. I'm not sure exactly how many I can say, but we have for production. Um, we have for a maintenance side as well as for kind of prototype development.
Okay, great, thanks. You all right? We're going to the next one, Rahul. Is that okay?
Yeah, no problem.
Yeah. Yeah. Can you say a few words about the corrections that you apply to your images? Asks William Ross.
Absolutely. So as I mentioned, a lot of we always save. So especially in the aerospace world, Daikandi is one of the key kind of things is to ensure that the raw image is always saved and is unedited, so that 5 years down the road, 10 years down the road, when you're doing an audit, you always have that raw image that you can always go back to and look at. So every kind of image correction that we do is on copies of that raw image. As far as the actual corrections that we do, it's primarily I'm not sure how familiar you are with actual kind of image processing algorithms, but the idea is to use pixel math and use looking at gray values pixel by pixel and then kind of clustering those iteratively. So you do one pixel at a time compared to its neighbors, then you do 4, then you do 9, and you kind of make kind of circles out and you cluster them together, and that's how we do the corrections. And then you're looking for correlations between, you start looking for edges, you start looking for, I mean, there's a whole lot of it, and we have a few papers kind of published about the algorithms that we're using. I'd be more than happy to kind of share them, but yeah, it's primarily looking at individual kind of points and then kind of clustering them together to get better ideas of what's going on in the overall part.
Okay. So you got a lot of R&D in that area? Rahul?
A tremendous amount, and we actually partner with multiple universities around the world in image processing. So we work with the Fraunhofer Institute out of Germany is one. We work with Stony Brook University, Worcester Polytechnic here in the U.S., with a couple of the IITs in India, with universities in China, well, a bunch of different universities kind of looking at next generation image processing. We also have multiple PhDs on staff that's what they do.
Okay, sure. All right, great. I've got a question here from Andrew Fay. Um,
Yep.
he wants to know what benefit do you see using Microfocus X-ray source tubes, and what's the ideal energy?
That's a good question. So a lot of as I mentioned, a lot of the lighter weight, lower density kind of materials that are especially used in the aerospace world do require kind of smaller focal spots to be able to pick out higher resolution and pick out the defects that are within them, and making sure that you're not kind of losing the defects because of focal spot or because of geometric magnification or anything else. So I would say that there's a tremendous benefit in using microfocus. There is no ideal kind of energy range. It all depends on the material that you're using. If you're looking at carbon fiber versus steel or versus Inconel, there's a whole different kind of range of energies that you have to use. We have to use the right source for the right job, right? So if you're looking at primarily steel kind of stuff and the heavier or even Inconel, and you're looking at more dense kind of objects, microfocus tend not to be as necessary, primarily because you have very low wattage coming out of microfocus sources, so it'll take a tremendously long time to be able to do that imaging. But if you're looking at lighter weight stuff, you do want that microfocus, smaller focal spot, less energy to come through, so you can actually ensure that you're looking through the part and not kind of burning through it with more powerful X-ray beams. So it's all application and part specific for which source and which energy to use.
Okay, great, thank you. I got a couple of questions here from Adrian Loggin, and then perhaps we got space for one or two more, time for one or two more. Um, Adrian wants to know regarding composites, are you able to detect fiber orientation in frames, in aircraft frames?
To some extent, yes. It depends on if you can do so. In order to do kind of fiber orientation, you have to get really small into kind of micron level, a few microns. So if we have the ability to do like a full kind of rotation around the frame, so assuming that there's nothing else kind of on the frame, uh, I would say yes. I wouldn't say 100%. I would say it depends on the orientation, it depends on the frame, and it depends on how much space we have around and what we can actually do with it. If you're doing a static kind of DR shot, it's more and more challenging. You'd have to use CT in order to get fiber orientation. And in order to do CT around a frame, I'm going to need kind of clearance on all sides and ensure that I have the right kind of resolution to be able to go down into that kind of micron level in order to see the fiber orientation. So,
Okay.
yeah, it's a little bit challenging.
Okay. He also wants to know about whether or not you're performing serial sectioning. I guess in some of the applications there, to validate image corrections and segmentation processes. Is that something that has to happen?
Um, yes and no. Again, it's customer specific. This typically occurs in when you're going through, proving out the system, proving out the corrections initially. So when we do preliminary kind of application studies, and then they will randomly kind of ask us to do this even on the production side. So the operators have to ensure that, um, you know, um, make sure that what we're measuring and what we're kind of enhancing actually matches up to real world. So they will use known kind of radiographic quality indicators, so known bad parts, etc., and making sure that our image processing can kind of pick it up and make sure that we're not kind of missing things that we're supposed to be picking up.
Great. Okay. Probably this is the last one from Arnold Becker. He wants to know, getting back to the X-ray, do you need time between X-ray shots because of overheating? If yes, how long? Can you give some numbers and talk around an example?
So when we design X-ray systems, we look at all of these, including uptime or what we call cycle time or load time on the source. Most of our sources we actually do introduce cooling whether it's into the vault using kind of air conditioning systems to ensure that it stays cool, ensuring that the source actually doesn't overheat. The sources do warn you if they are getting too hot, and they will automatically shut down, so you can't burn them per se because of overheat. They use oil to kind of cool most of these, and they have pretty specific kind of tolerances that are built in. So the software is pretty intuitive, and it will warn you if you are overheating. We don't necessarily see overheating too much unless we're running like a 24-hour scan, a CT scan on some object. Even then, we haven't really noticed it, primarily because we design our vaults and our systems with that in mind, to ensure that we can kind of keep the environment at a cooler temperature using either air conditioning or using anything else to do that. Um, the detectors do also drift, so we've seen that for, a lot. There's offset drift, especially as temperatures, electronics are sensitive to temperature. So if there is an environment where this will start to happen, we actually have recommendations that you do new offsets or you do some kind of cool down period, but it's rare that we have to do that.
Okay, right. Thanks. That's great. I'd just like to remind everyone that this whole presentation, including the Q&A session, will be available to view online on demand after this. Probably, I don't know if it's immediately or by tomorrow, but if you want to review any of the information, it'll all be there accessible via the Aerospace Testing International website. I think we've got time. Just one last cheeky question from me. Actually, I was quite interested to I was quite interested to hear you were talking a little bit about reliability and calibration and checking the machines and stuff. I don't often hear you guys talk about that. Is that? I mean, how often do one of your machines? I know they can vary so much in size and what they're doing, but is that something that has to be done frequently, or I mean, how often do things have to be calibrated and checked at the start of every session?
So yeah, we typically like operators, especially in between each shift. Let's call it, we like them to do a calibration before each shift. And if they're doing multiple scans, it depends on the customer or the actual user. But most of them prefer at least once a shift to do a kind of calibration scan. So typically at the start. Sometimes in the automotive world, we actually do it at the start and every hour. And so then if something kind of goes out of whack within that hour and it's not matching up, you only have a certain number of parts that you have to pull out for reinspection. If you do it shift to shift, and if something goes on, you might have to pull out an 8 hours worth of production, which is not necessarily more fun. In the aerospace world, because it's typically fewer parts than in automotive, shift to shift seems to be okay. Yeah, it really depends on the number of parts and all that. But yes, we do recommend it. We actually build it into our software. So we actually give, depending on the frequency that the customer wants, the software will actually shut down the system and say, you can't operate anymore until you do a calibration scan, depending on the frequency that the customer wants.
Okay, great. That brings us up to the hour, so I'm gonna draw the webinar to a close there. Thanks so much, Rahul. It was really interesting, and I think I saw the numbers of attendees actually increase as you were talking, which is
always a good thing.
It's a good thing, right? Yeah, it's great. I don't often see that, so thank you, and thanks everyone for attending as well. We appreciate your time. I don't know if you want to wrap up, Rahul, or say anything else. Or...
I just want to say thank you guys. And if you have any other further questions, feel free to reach out. But thank you, and we look forward to doing this again. Thank you again. Thanks, Ben.
Great. Cheers. Thanks.